Hi guys, Shouvik and welcome back to YouTube channel. So today we'll solve another question from Leetcode itself. So let's get started. Yes, so today we have this question: find minimum time to reach last room. Yeah. So first we will understand the problem statement. We will go through the problem statement first to try to understand it. So yeah, there is a dungeon with n cross n rooms arranged as a grid, right? They have given to us, and you are given a 2D array move time of size n cross m, where move time of ij represents the minimum time in seconds when you can start moving to that room. So please take a note. So move time of ij is stating when you are standing to a when you are standing to a particular cell. When you are standing to a particular cell, what is the minimum time needed? What is the minimum time needed so that you can start moving the cells? You can start moving the cells. So this line is actually the main fundamentals, or I have to say the entire like execution logic is basically hidden to this line also. If you are not going to understand these lines, you are not going to get an AC for sure. So I personally feel the English they have written is not on the good path, and on discussions also people are like started quarreling on that part on. But yeah, I will make the lines easy for you to understand. But yeah, first we will complete the readings of the problem statement, then I will go back to these lines and will explain it in the one. Yeah. So and they have given you can start from room 00 at time t0. So that we are starting from room. Which room? We are going to start from room 00. We are going to start from room 00 with what times? At time t equals to 0, and can move to an adjacent rooms, and can move to adjacent rooms. Moving between adjacent rooms takes exactly 1 second, and you can move to any adjacent rooms like 4 directional rooms. So here you can see 2 rooms are adjacent if they shows a common wall either horizontally or vertical. Either horizontally they are sharing or vertically they are sharing. So you can move on that directions at t equals to 0, and can move to an adjacent rooms. Moving between adjacent rooms takes exactly one second. So when you are moving from one cells to another any adjacent rooms of 4 directions, then it is going to take one more second. And finally we have to return the minimum time to reach room n-1 and n-1 that we have to return. So first we will try to understand what they are basically stating by this rule, where move time ij represents the minimum time in seconds when you can start moving to that room. So that is a minimum time when we can start moving to that room. So now we can go to our one note to try to understand that line specifically. So today our one note is working, or how it is? Space one. If I get please make connections first. This is 5G. This one is another 5G only. Yes, it started working. Okay. So what I am stating, I am basically telling you guys that when if I can go to very bottom and at very left, that is the identical points to do the diagram. Right. So what happens now? Am I able to write? No, I think there is an issue. I can add a page, untitled page, that would work. And on this untitled page, we can start from very top. I think this page we have completely occupied with all the diagrams. Yes. So what I am stating, let's suppose we more thick is we are right. Yes, it is coming like this side would be fine, right? So if let's suppose we have this grid, we have this grid. So when you are standing, let's suppose at this point, and you want to move, let's suppose to these cells, you want to move to down cells, and let's suppose you are standing at this particular cell with a value at let's suppose at t equals to 3. You are standing at this particular cells, and let's suppose the value at this particular cells is 5. The value at this particular cell is 5. That is the minimum time to visit that cell. Minimum time when someone from any other cells which are like 4 directionally connected to it can start to visit. So 3 is not equivalent to 5. So 3 at t equals to 3 we can't visit. So we have to wait. We have to wait. So at t equals to 4, at t equals to 4, at t equals to 4, can I start moving to it? Can I start moving to it? T equals to 4. No, still 4 is less than 5. At t equals to 5, at t equals to 5, can I start moving to that cell? Can I start moving to that cell? Yes, because the value is now less the time when you are trying to visit that times that t is my greater than equals to the mean time. My current t, if I am considering 5 as a, if I consider this 5 as in my mean time and the current times is this t, so t should be greater than equals to my mean time. T should be my greater than equals to my mean time when I can start to visit to that cells, right? We can start to visit that cell. So t equals to 5 we can start to visit that cell. But when we are going to land on that cells, when I can say that okay, I am at this particular cells, I am at this particular cells, right? When I can say I am at now and on that particular cells, t equals to 5 we are just moving to that cells. And now we know to move to a particular cells from move to land, from move to land to a particular cells is going to take 1 second, is going to take 1 second. So at t equals to 6, at t equals to 6, I can say I am at land to this particular cell successfully. So at t equals to 6, I can say I am land to that cells successfully, right? So now you can go to understand the test cases, you can get the field. Otherwise, on if you are not able to understand that particular one note explanations, you are not going to get the gist of this particular problem. So here you can see, like we at t equals to 0 we are at 0 0, right? At t equals to 0 we are at 0 0. The minimum time required is 6 seconds. How? So we can visit that 4, like here you can see it's on 2 directional, like on 0 0 we can either go down or we can either go right. So on right it has 4 and on down also it has 4. So at t equals to 4, move from room 0 0 to 1 0 in 1 second. So that is the beauty. So you maybe think like at t equals to 4, you land on these cells, you land, sorry, not on these cells, they move to 1 0, they move to these cells, right? They move to down, so they move to at t equals to 0, sorry, t equals to 4, they move to at 1 comma 0 cell. No, not that. At t equals to 4, they started moving from 0 0 to 1 0, but when they land to this particular cells, after consuming one more second, I think you guys are getting the feel now. So at t equals to 5, they land to this particular cell, so at t5, move from now at t5 they just landed and they can move from 1 0 to 1 1, from 1 0 to 1 1. So from here to move here, so they have landed to this particular cells, which I am highlighting at t equals to 5. And now 5 is greater than equals to 4. 5 is great. So we need to go to these cells. So when we can go, so the value, the current time should be greater than or equals to my mean time, right? So my mean time. So at t equals to 5 is greater than equals to my 4. So they can move. They obviously can move. So at t5, they move from 1 0 to 1 1. But when they can reach to 1 1 after consuming one more second. So at 5 plus 1, at 6 seconds, they can successfully land to this 4th cell. I guess now you guys got the gist of that problem. So here you can see on this particular examples, the minimum time required is 3 seconds. They can at 0 0, from 0 0 to 1 0, they have moved up with consuming 1 second. T equals to 1, from 1 0 to 1 1 in 1 second. From t equals to 2, they move from 1 1. So that means 1 1 means these cells to right at t equals to 2, but they need 1 more second. So that's the reason the answer is 3 seconds. Now I think you are getting the transitions, how when we can move, when my time is altogether, the current time is altogether greater than or equals to my mean times, then only we have the liberty to move. And to land successfully to that particular cells, I am going to consume 1 more second. So when I can say I have reached to a particular cells, what they are looking for, they are basically looking for when we are land to n-1 and m-1. But when I can say I have successfully land to a particular cells after, so we can't say when we have the liberty to move, we have land to that particular cells. No, not that. When we have liberty, then we can start moving, and from start to reach we need 1 second. So whatever the liberty plus 1 seconds, you have to consider as a successful land to that particular cell. So that's exactly what they are basically setting, minimum time in seconds when you can start to moving to that particular routes, right? Yes, I think the problem statement is bound to be clear to you guys. If not, then I will definitely suggest please go to that one note explanations one more times if you are not going to get the gist on the first one. Yeah, so our n can grow as big as 50 and m can grow as big as 50, and move time is in the range of 10 raised to the power 9. So tell me guys, like just seeing these problems, what actually is coming to your brain? What actually is coming to your brain? So now, if I can again go to the one node, now we can start on the intuitions building part. How you can find the algorithms, the known algorithms you can try to fit to this particular problem. So we have a grid. We have a grid. So tell me guys, these cells, how many times you can visit? So you are going to start from here. So you can move here and you can come here. You can move here and you can come here, right? So how many times these particular cells can be visited? How many times these particular cells can be visited? In general, I can write it more than one times, or more than or equals to more than equal one times. Also you can go to this and then come to this, that is also a successful visit, but out of them, let's suppose you start at time t equals to 0. So for this particular cells, everything is 0. At time 0 you are at 0. So let's suppose the cost to visit this particular cell is 7, and for this particular cells, let's suppose 2, and for these particular cells, let's suppose the minimum visit time is 1. So if we are running standard BFS in a grid, so maybe we are going to consider this 7 path. Then it is my current times is going to be, when I am going to land to these particular cells, my current times is going to be 8, because 7 path we can start moving to that cells, and to land it successfully we need 1 more seconds. So on 8 we have successfully land to these particular cells, right? We have successfully land to this, and from here we need 1 more seconds to move down. So at current time as 9 seconds, I am able to land to this particular cells. But if I take the below route, so for the below route, I reach this particular cells at current times equals to 3, because at 2 I can start moving, and at 3 I have successfully landed, and at current times equals to 4 I can successfully land to this particular cell. So I got a good answer of to visit that particular cells at 4 seconds. But here we are getting time of 9 seconds. But we are looking for minimum. So that is going to be the optimal solutions. This particular visitability arrangement is going to give you the most optimal solutions. So for every cells. So now I think you guys should be aware to correlate. So if it is a standard BFS, then what we will do? If it is a standard BFS, then I am again drawing the grid. So either you can take this path or you can take this path. So you are going to start with a visited array. And you can mark it when it is going to be visited on very first time. But with this path, our answer is non-legitimate. We are going to get our answer on this path because the cost is less. So to move, so when we can use the standard BFS, when to move for every movement have uniform cost. Every movement, when we can use standard BFS, every movement should have, tell me guys, uniform cost. But for our case, we just saw one path is taking more cost, another path is taking less cost. So that is a standard BFS. Now if our cost is non-uniform, if you have a weighted graph with non-uniform weight, some path have weight 10, some path have weight 2, some path have weight 19. So what is the minimum time? So when you have a tell me guys, you should be aware, you should be able to tell this. So when you have a weighted graph, and with first things is the graph should be weighted. So these conditions satisfied. Second conditions, they are asking for minimum. So which algorithms is coming to your brain? When we have a weighted graph and they are looking for minimum time from single source. Do we have single source? Third point is single source. Do we have single source? Yes, we are starting from 0, 0. So we have single source validate. Minimum time they are looking for. The graph is weighted. Another one is single source. What they are looking for? Single source sorry, this is should not be considered as a defined point. Single source, shortest path, single source, shortest path of n minus 1 and m minus 1. Yes, they are looking for this only, single source from 0 0 to n minus 1 and m minus 1. This path they are looking for. Single source, shortest path algorithms, weighted graph, minimum time, which algorithms? You should definitely tell me, guys. It is nothing but Dijkstra. JKSTRA, Dijkstra algorithms. So you saw, right, how just by writing few more test cases, just by doing few more pen and paper work, we have reached to a well-known, our popular digested algorithms, that is Dijkstra algorithms. So I have already made a detailed video of our own template of the Dijkstra. So if or at any particular times you are not able to understand the templates that we have used, you can go to that video and come back to that video. You will definitely get the gist. But for this particular video, I am not going to explain my template. I am just going to, but yeah, on high levels, I will give you the overview what actually the each lines of the code is doing. But on Dijkstra line by lines intuitions, I am not going to give you. I am just giving you that on this particular video how you can match to a known algorithms that you have already solved. You have already solved problems on Dijkstra. You have already know Dijkstra template. How you can fit your Dijkstra to this particular problem. That intuitions I am just giving you. So I guess you guys got it. So now we can just go to the code iterations. There is nothing on the code. I have exactly written my own template. I have exactly written no like over complication, nothing. I have directly written my own template. Yes. So I have started my n and m to be len of move time and len of move time of 0. That is the number of rows n, number of columns m, and I have initialized with a heap that we need a priority queue or heap queue to do the Dijkstra, to run our Dijkstra. And I am pushing the value heap queue dot heap push. What we have to push, what by what basis we have to visit a particular cells. What is the minimum times we can reach to that particular cell? So first 0 is stating what is the current times, what is the minimum current times we can explore to this particular node. Second one is the indexes, like ij is the indexes, xy you can consider, ij you can consider, that is the row number, that is the column number. Now this is the min time. Now I have initialized my Dijkstra tables with min times of sys.maxSize. You might solve like 1D Dijkstra, but that is of 2D Dijkstra. There is no super magic. You can just initialize your Dijkstra with a 2D grid. That's it. Other exactly same things. So I have did exactly same. Sys.maxSize. We have initialized everyone to be at maximum size, and that's it. And now we are just popping the value. So we are running a for loop while len of HP, right? And we are popping the value heap queue dot heap pop HP. So the first value is the current times. Second one is the x row number, y is column number. Now I am iterating to 4 directions. I have to explore the four directions, right? Because all are adjacent. 4 directions I have to explore. So for dx dy in 0 1 1 0 minus 1 0 1, that is our known template, guys. So please, so that's the reason I am repeatedly requesting to you guys, please go to that Dijkstra playlist or graph playlist at least to find the Dijkstra video. So you have detailed explanations on the Dijkstra template that we use. Yeah, so now we have to just check if my x plus dx, that is the new index that we are trying to explore, is within my row boundary. The new column index that we are trying to explore, y plus dy, is within my column boundary. And what is the next time to consider? So now if we can go to our one node, I think I have already shown, but yeah, for sake of simplicity, I can again draw a grid. So let's suppose you are here at current times. Your current time is 2, and to explore this particular cells, you must need minimum of 5 time. Min time is 5. So when you can say you should be able to explore, so your next time to consider should be, on that case, is 5 plus 1. So on that times or 6 at time 6, can I say I should be able to land to this particular cells. But now consider this as a value of 1. Let's consider this as a value of 1. Instead of 5, let's suppose the value is 1. Right? So on that case, what is my next time to consider if the value is 1? So when I am at this index at 2, so just I can start moving, because the value, what is my current time, is greater than the minimum time they are looking for. So I am already good to move. But on that case, I have to wait till my current time become 5 seconds. I have to wait silently there. But for this case, I can start moving, and for move I need 1 second. So that times my explorations times is become my current time plus 1, that is of 3. So what is the next time to consider if I am trying to generalize both? If I am trying to generalize this both, so if my next time is greater, I am doing next time, if the mean time, sorry, if the mean time of the next cells that we are trying to explore is greater, then I am doing that particular cells plus 1. And if my current time is greater, then I am doing current time plus 1. So I can take a max of both. Max of whom? Max of my current time, either my current time or the mean time of that particular x plus dx and y plus dy vertex. I can take that and do a plus 1 and can store in a next to consider in general, because here we are basically doing what is the max of both. Plus 1 we are doing, and that is the plus 1 we are doing. Exactly same things I have done here. So next time to consider is max of either my current time or move time of x plus dx, y plus dy, either of them, and plus 1, because we need 1 more seconds to successfully land to that particular x plus dx, y plus dy cell. Now we have used the standard Dijkstra things. If that next time to consider with the value, let's suppose, now if we can go again to the OneNote, I personally feel I don't need to explain this. That is the standard template after that I have followed, but for sake of simplicity I am just going to quickly explain it. So if let's suppose this cells is already explored with some lesser value, which variables I am storing it? Mean time. On this mean time variables I am storing. So let's suppose if my mean time variable, so with this current configurations, what is the current configuration from this to this? That is the movement we are trying to make. This is the movement we are trying to make, which I am repeatedly highlighting. This one movement is, but let's suppose there is a path like this. This in which we have visited this mean time of whom? X plus dx, and what is the new cell? Y plus dy, right guys? Y plus dy is already my smaller, less than equals to the next time to consider. That is the current way we are trying to explore. We have stored it is next time to consider. That is the best we can achieve with current exponentials. If it is already greater, then do we need to do anything? No, because we have already explored that particular cells with some lesser value, so that my mean times is already updated with some lesser value. So we are only going to update to our mean times only if we are only going to consider this particular path. When it is greater than, when it is smaller, when my next time to consider is smaller, not smaller than equals to it's completely like this arrow is going to be on reverse side, so it is kind of greater in that sense of mean time of x plus dx and y plus dy. What is the value that we have already explored that particular cells is greater than my next time to consider. We have find a path with next time to consider with some more smaller value. What is the mean time is storing? So we definitely update my mean time of x plus dx of y plus dy with this mean time to consider, and have to push this particular value to our hip queue. Exactly same things mostly we are doing. Yes, we are updating it with next time to consider, and we are pushing to my hip queue with next time to consider this, and that is the cells that we are going to explore, x plus dy, y plus dy. So that is the very naive standard of my own Dijkstra template that I have followed, and we have successfully got an AC on the very first. And finally, our answer should be going to be updated mean time of n-1 cells, right? Because single source shortest path. So from this particular source, that is of 0, 0, what is the minimum time to explore any node is going to be stored to that particular index, that particular node value. So for our case, the node value is n-1, so we can return this. Yes guys, so the problem is as simple as that, and now we can quickly discuss the time complexity. So on time complexity, these particular things, definitely you don't have to things very in depth to discuss the time complexity. That is the very common Dijkstra time complexity. So if we can Google it out, you can find it like Dijkstra time complexity. You can just mention the Dijkstra algorithms time complexity. Some log factors, I think big of v plus e log v. So that is the time complexity of Dijkstra. Yes, I remember. Big of v plus e log v. So you can mention this. It's more than sufficient. That is the time complexity of general Dijkstra. And for our case, what is this v? So we have total 50 cross 50, right? Now I can write it. Your v can go as big as 50, and your edges, how many edges you can have. So you could have for every cells you have four options, right? So but for the surrounding cells which are boundary cells, for them like you have two options only, either up or down, either up or up down, right? Only two options, right? For the boundary cells, and for middle cells you have four options. So I'm considering four directions only. So 4 into how many cells you have, that is of 50. So your E can be as big as like 4 cross 50, but it is much more smaller than this. So you can put this D is 50 and E is 4 cross 50, and you can get your final times that is going to be it. But it is like very optimized, so that is the most optimal solutions you can achieve. And for space complexity, what is the space we are using for Dijkstra? That is the general space, like min times array we have to store it. For our case, it is becomes a grid. So big of V square, and your V can be, I can write it kind of like this, big of V square, because that is the space we are going to consume. Or in a general, I can write it n plus m. That is the number of rows to number of columns. That is the space of the view. Yes, guys. So the problem is as simple as that, and I'm pretty sure that is the most optimal solutions that you can achieve of. So my submissions is almost like 90% faster than all the Leetcode submissions over happened. So that is bound to be the most optimal solutions that you can achieve for this particular video. And if you guys are able to understand till this point, so please do subscribe to the channel, and please share the videos to your friends circle who are also preparing for top product based company and who are also brushing up their cases. And please turn on the notification so that when we are going to live to our next video, you get the notification as soon as possible. So that's it, guys. That's it today. That's it for today. Let's meet tomorrow with another beautiful person. Bye, guys. Bye.